Welcome to lesson 4.7.3, and in this lesson we will be looking at double angle identities. Given that 1 minus sine squared divided by sine of 2x is equal to 1/2 the cotangent of x, A. Algebraically prove the identity, and then B. Determine the non-permissible values in radians for the identity.
Okay, so we're going to prove this identity here. And notice we've got the double angle showing up in here. So we're going to split this up into left side and right side. On the right hand side we've got this 1/2 cotangent of x. Now we should note right away here, because we know that this is an issue, and actually the next question here is about determining the non-permissible values. So let's kind of do everything together here. We know that on the right hand side here that for cotangent here, x cannot be multiples of pi. Okay, because again, sine is in the denominator in cotangent, and that's going to be equal to 0 on multiples of pi. Now let's take a look at the the left-hand side here. Actually, we've got a couple of identities that pop out immediately at us. Notice that the numerator is a Pythagorean identity. 1 minus the sine squared of x is going to be equal to the cosine squared of x. And the sine of 2x is 2 sine x cosine of x. Now, on the left-hand side, there's a common cosine there that I can cancel, and this becomes, what do we got here? We got cosine of x over 2 sine of x. Now, that is true as long as cosine doesn't go to 0. And cosine goes to 0, okay, at x, sorry, I'm going to give myself a little bit more room here, okay. We can say that, this is going to equal 1/2 the cosine of x over the sine of x, so long as x does not equal pi over 2 plus n pi, where n is an element of the integers. And I know that ran over to the side there, but anyway, you get the idea here. And at this point now I can say that we know that cosine over sine is going to be cotangent, so this is going to be 1/2 cotangent of x. This does have the restriction on it because the sine is in the denominator. It does have this restriction that x can't equal to n pi, but we've also got this restriction here that x can't equal pi over 2. Okay, because if it equals pi over 2, then we're going to have an issue in the denominator here. So really on the left-hand side here, we've got here x cannot equal multiples of pi over 2, where n is an element of the integers. And so again, it's so close, but it's not exactly an identity. So what we might state here, okay, what we might state is that 1 minus the sine squared of x over the sine of 2x is in fact equal to 1/2 the cotangent of x if, okay, as long as, x does not equal, now what I got to address here is where they're not equal to each other. Okay, where are these two not the same? And the answer is they're not the same at pi over 2 plus n pi, where n is an element of the integers. This is a restriction on the left-hand side, or one that comes out of the left-hand side that does not pop out of the right-hand side. And so that needs to be stated in order to really make this a true statement. Now, let's just take a real quick look here at the part B here where it says determine the non-permissible values. Well, we have already done that. Okay, we know that overall it's n pi over 2, multiples of pi over 2, okay, again, where n is an element of the integers.
Given that the sine of 2x divided by 2 sine squared of x is equal to the cotangent of x, A. Algebraically prove the identity, B. Determine the non-permissible values in radians for the identity.
Okay, once again, let's take a quick look at the question here where we're proving an identity. Now, and again, we've got the left-hand side and the right-hand side here. So on the right-hand side, there's really not much I can do except identify that it's the cotangent of x. What I will do, though, because again, the second part of this question is about identifying the non-permissibles, I'm going to identify the non-permissible, and it's going to be that x cannot equal multiples of pi. Okay, where n is an element of the integers there. Now, on the left-hand side, what have we got here? Well, we've got that double angle identity up in the numerator. The sine of 2x here, and so that's going to be the same as 2 sine of x cosine of x. And then the denominator will be 2 sine squared of x. Okay, and then I can cancel the 2's, and I can cancel one of the signs here, and I'll be left with the cosine of x over the sine of x. Now I cancel the signs, and I can only do that as long as I state that x can't be equal to n pi, where n is an element of the integers. But you know what? That is totally okay, because that was a restriction on the right-hand side anyway. So it's a restriction here, it's a restriction here, it's the same restriction on both sides. That's wonderful. Cos over sine is in fact cotangent, and we've got this lingering x can't equal n pi, where n is an element of the integers. That's the same on both sides. This is wonderful. I don't need to state anything else. That is an identity. It is the same for all values. It's even undefined at the same values here. And we've already addressed what the non-permissibles are here. We know that x cannot equal multiples of pi. Okay, that's where the denominator goes to 0. That's where the function becomes, or the expressions become undefined.
Solve the equation 4 sine squared of x minus the sine of x is equal to the cosine of 2x plus 1, where x is between negative pi and 2 pi.
Okay, so we're going to end trigonometry here by looking at a small handful of equations here. Here's our first one that we're going to solve. And these are about as difficult as these equations will typically get. Okay. Now the first thing we want to do is take a look at our domain once again. Negative pi out to 2 pi. And so let's just identify what that means to begin with, okay, along our coordinate plane here. Negative pi, once again, refers to that negative half rotation, whereas the 2 pi corresponds to a positive full rotation. So this is the domain in which that I'm looking for my solutions. Now let's take a quick look at the equation here. Right away, there are two major problems with this equation. First of all is that I've got a sine and a cosine in it, two different trig functions. Now, unless I can factor those apart, that's actually a problem. If you can factor them apart, it's not a big deal. Then you just do that, and then you solve the individual pieces here. But in this case, this is a problem. Now, additionally, it's the cosine of 2x, whereas this is the sine of x here. So that 2x is also a problem. Even if this was the sine, because this is 2x, I would still be running into a bit of difficulty here. So this cosine of 2x is really the problem here. Now, I can get rid of the cosine of 2x simply by using an identity. But with cosine, there are three different identities that I could possibly use. There's the cosine squared minus the sine squared. It's the 2 cosine squared minus 1, or 1 minus 2 sine squared. Well, the one that I want to use is the one that only introduces a sine, because that's what I'm seeing here. So that's the one I'm going to use. So this will be the 4 sine squared of x minus the sine of x is going to equal 1 minus 2 sine squared of x plus 1. Now the whole thing is in terms of sine, and not only that, they're all sine of x. There's no sine of 2x. Now I'm going to bring everything over to one side, so I'll bring the sine squared over. So this will be 6 sine squared of x minus the sine of x. And then I have the 1 plus the 1 there, bring that over to be minus 2 on the left-hand side. And now this is just a quadratic, a pretty straightforward quadratic that can be factored actually pretty simply. The factors of 6 here are going to be 2 and 3, so it'll be 2 sine x, 3 sine x, and then what do we got here? This needs to be negative, positive. Okay, so it's going to be negative 2, looks like, and then plus 1 to finish that off there. So we've got now two different factors here, each of which could go to 0. This will go to 0 if sine is equal to negative 1/2, and this one will go to 0 if sine is equal to positive 2/3. So now let's solve this here. Where does the sine become negative 1/2? Well, that's going to be true in quadrants 3 and 4. Okay, so this is going to be true down here in quadrants 3 and 4. What's my reference angle? The reference angle, I'll find that by doing the inverse sine of the absolute value of negative 1/2. Okay, and since we're in radians here, I can tell you that's going to be pi over 6. Now, again, my solutions are in quadrants 3 and 4. Now, look at our original domain here, though. That means I'm going to get 4 different solutions from this. So, one in the 4th quadrant, one in the 3rd quadrant. Now, rotating this way along that negative 1, okay, I'm going to identify the two different quadrants here. So I'm going to have x in the third quadrant, and then I'm going to have x in the fourth quadrant. Well, first of all, when I rotate negatively into that fourth quadrant, that angle is going to be negative pi over 6. It will be the same as the reference angle. And when that pi over 6 is out here in the third quadrant, again rotating this way, this is going to be negative. Well, it's not quite a full pi. I'm one less. It's going to be negative 5 pi over 6. And now that is all that I can see on the negative part of that domain. So now I'm going to come back up here and I'm going to look at the positive part of the domain. Remember, I'm still going into the third and fourth quadrants here. So to come around here, this is going to be 6 pi over 6's, because that's a full pi. And I'm going to have one more to get into the third quadrant. So my additional angle here is going to be 7 pi over 6. Now there are 12 pi over 6's in the full circle here. So to get into the fourth quadrant, I want to go through all of them except for one. So that's going to leave me with 11 pi over 6 to get into the fourth quadrant along the positive part of the rotation. Good. Now, I go to the second function here, the second part of this problem here. Sine of x is equal to 2/3. And once again, okay, I'm looking at sine. Okay, they're both sine functions here, but this time sine is positive, and I know sine is positive in quadrants 1 and 2. And when I look at my domain here, 1 and 2, I'm only going to get the two solutions. Okay, there's not going to be doubling up there, just one of each. So the first thing I'm going to do is figure out what my reference angle is, and that'll be the inverse sine of 2/3. Now, because that's not a unit circle ratio, I'm going to have to go to the calculator to figure that out. And so I'm just going to round that. That is going to be approximately 0.73 as my reference angle. So now when I give my answers here, I'm going to leave the full decimal in my calculator, but my answers are going to be approximate. So my first quadrant answer is going to be the same, okay, as the reference angle. That's the beautiful thing about quadrant 1. My second quadrant angle is going to be pi minus the reference angle. Okay, I'm going to go over here and then I'm going to lose that reference angle. So it's going to be pi minus that. And again, that's going to be approximately 2.41. And so right there, those are all of the solutions that I expect for this particular equation.
Solve the equation 4 sine squared of x plus the cosine squared of x is equal to 4 cos x, where x is between 0 and 360 degrees.
Right. Here's another equation that's going to require some identity substitution in order to solve it. The very first thing I want to look at, though, again, is the domain over which we're working. And this is a nice one. It's just 0 to 360. So we're in degrees, and it's just a full rotation around. Now let's take a look at what we got here. We've got sine and cosine. Now everything is in terms of x, and that's great here. But I've got sine and cosine together, and I can't separate them by factoring. Okay, so I'm going to have to do a substitution here. Now, you cannot make this sine squared plus cos squared equal to 1. I know that's what it looks like here, but it's not sine squared plus cos squared. It's 4 sine squared plus cos squared. I had to multiply the sine squared by 4 first. So that's not actually the identity. Now, I'm still going to use that identity, but I'm only going to use it in parts here. Notice that I've got cosine here and a cosine here. It's the sine that's the different one. So what I'm going to do is I'm going to use that sine squared plus cos squared equals 1 identity to replace the sine squared of x. And so this will become 4 times 1 minus the cosine squared of x plus the cosine squared of x is equal to 4 cosine of x. And now I'll expand that out. And now everything is in terms of cosine. And what I'll do here is, because the cosine squared term, okay, even when I add those together, I'm going to get negative 3 here, cosine. It's negative on this side. I'm going to bring everything over to the right-hand side, just so that the cosine squared term is positive. So this will become 3 cosine squared of x. What do we got here? Plus 4 cosine of x minus 4 is equal to 0. And now what we'll do is we'll factor that. It'll become 3 cosine of x, cosine of x. And now what do we got here? We need this to be 4. So I'm guessing the factors are going to be 2 and 2. Let's just double check that that actually works. So this will become 6, 4, and that works as long as this is positive and this is negative. Which means that the values of cosine can either be positive 2/3 or negative 2. Now, what I like about a problem like this is this one right here. I'm going to look at this one immediately. I'll come to this one in just a second, but this one, that's a dead end. Cosine never does become negative 2. Okay? Its range is only from -1 to 1. So there's going to be no solution coming from that factor. Now, there will be a couple solutions from over here. Cosine is positive 2/3. That means I'm going to have an answer in the first quadrant and the fourth quadrant. I'll figure out my reference angle by doing the inverse cosine of the absolute value of 2/3. And because, again, that's not a unit circle ratio, that's a little different here. What I'm going to do here is do this approximately. This is approximately 48 degrees. Okay, so that means in my first quadrant, that 48 degrees is going to be 48 degrees approximately. And then I have to put that into the fourth quadrant. And so that'll be 360 minus your 48. And again, it's approximately 48. So this is going to be approximately 312 degrees. And so those are the two solutions that I'm looking for, 48 and 312.
Solve the equation sine of 2x is equal to √3 sine of x, where x is between 0 and 2 pi radians, and then verify graphically.
All right, one more question. So here we go. Solve sine of 2x is equal to √3 sine x. Okay, and again, we're going to get to this in just a second, but let's look at that domain. Okay, 0 to 2 pi. Now, again, the nice thing about something like that is just a positive full rotation. So that's it. That's all we're looking in. Okay, now let's take a quick look here. Sine of 2x is equal to √3 sine x. I can't do much with that because this is sine of x, this is sine of 2x. The arguments are different, so they're not really the same trig function. So I got to do something to get rid of or to change that. And this is the one I'm going to change. Now, there is only, however, one identity for that, and that's going to be 2 sine x cosine of x is equal to √3 sine of x. Now, that has introduced a cosine function. So now I've gone back a couple steps here in a sense because I was telling you in one of the previous questions that, well, you can't solve it if you've got two different trig functions in there. Unless, and this is the key to this problem, unless you can factor them out. Now, there is going to be a temptation for some of you to cancel out the sine of x here. But you don't actually want to do that because you're going to lose solutions if you do. Okay? You can cancel coefficients, you can cancel numeric values, but you don't want to cancel anything that's got a variable in it. Instead, what you want to do is you want to bring that over. And so this will become 2 sine of x cosine of x minus √3 sine of x is equal to 0. And now what we want to do is factor that. So the sine of x multiplied by 2 cosine of x minus √3 is equal to 0. And this gets us two different equations here, okay, because corresponding to the two different factors here. Either the sine of x is equal to 0, or the cosine of x will equal √3 over 2. Okay, and individually these are fairly easy to solve. So we have the sine of x is equal to 0, and we know where that occurs, okay, because sine is going to equal to 0 anywhere on that unit circle where the y-coordinate is equal to 0, and that's going to be where the angle is either 0 radians, pi radians. Now I would go so far as to say 2 pi, but if you look at the domain that we're given in the equation here, we're not including 2 pi. It's less than 2 pi. So that's it. That's as far as that goes. So we only need to write 0 and pi there. Now let's take a look at the second factor here. Cosine of x is equal to √3 over 2. Okay, well that's positive. We know that that's going to occur for cosine in quadrants 1 or 4. Now we'll figure out the reference angle, but that's actually pretty easy to do as well because we know that cosine goes to √3 over 2 when the reference angle is pi over 6. So now we just have to put that in the two corresponding quadrants there. And so that's going to be in the first quadrant, pi over 6. That's the easy one. And in the fourth quadrant, okay, well in the fourth quadrant, when you come all the way around the full circle, that's 12 pi over 6s, but we're short one in the fourth quadrant. So that leaves us with just 11 pi over 6s. So here are our answers, okay? 0 pi, pi over 6, and 11 pi over 6. Now the question also asks us to verify this is true using the calculator. Now we're just asked to verify that this is true, so I'm going to do this graphically. Okay. So what I'll do here is I'm going to graph everything over to one side of the equation. So sine of 2x minus the square root of 3. Let's get out of there. Sine of x. I'm already in radian mode. Now what I'm going to do is I'm going to adjust my window settings here. Okay. My minimum here is going to be 0. And my maximum is going to be 2 pi. That's going to mirror what I've been told in the equation here. So there's 0 to 2 pi. But what I'm going to do specifically here, I'm going to do myself a little bit of a favor. I want my scale to go up by pi divided by 6. Okay? Because my answers look like they're going up in terms of multiples of pi over 6. My y min in this case here could probably stand to be just like -5 and then +5 for the maximum, just so I can see a little bit on either side here. And when I graph that, you can watch it grow here and drop back down. Now, I could have probably zoomed in a little bit on this to see it a little bit better, but here you're seeing the answer here. It is intersecting the x-axis right there at the origin. It goes up, and then at pi over 6 it goes through. So that's 1, 2, 3, 4, 5, 6. Pi over 6 is going to be pi, and that was one of the solutions we had. 7, 8, 9, 10, 11, and that's where we hit the x-axis again. And we would hit it at 2 pi, but again, we're not including that. So yeah, my graph here does in fact verify the solution that I just found. There we go.